Welcome to Synapse Global Institute. I am Alina, your lecturer for quantitative analysis, and today we continue our work by focusing on descriptive statistics, beginning specifically with measures of central tendency. This topic is fundamental to business analysis because it equips us with tools for summarizing large datasets into single representative values that support interpretation, comparison, and decision-making. As we move through the material, please remember that you are encouraged to use the chat section at any time to ask questions or seek clarification. Measures of central tendency are statistical measures used to describe the center or typical value of a dataset. Rather than analyzing every individual observation separately, these measures provide a concise, numerical summary that reflects where the data are concentrated. In business, accounting, and finance, measures of central tendency are used to analyze sales figures, costs, prices, wages, returns on investment, and many other quantitative variables. The main measures of central tendency covered in this section are the arithmetic mean, the weighted arithmetic mean, the geometric mean, the harmonic mean, the median, and the mode. Each measure is suited to particular types of data and analytical situations, and understanding when to use each one is just as important as knowing how to calculate it. We begin with the arithmetic mean, commonly referred to simply as the mean. The arithmetic mean is defined as the sum of all data values divided by the number of data values. The mean is equal to the total of all observations divided by the number of observations. This measure is the most widely used measure of central tendency because it takes every data point into account and provides a balanced average. In business contexts, the arithmetic mean is frequently used to calculate average sales, average costs, average revenues, and average profits over a given period. To illustrate the arithmetic mean, consider a dataset representing monthly sales, measured in thousands of units, for a company over 5 months, given as 10, 12, 14, 15, and 18. To calculate the mean, we add all the values together to obtain 69, and then divide this total by 5. The result is 13.8. This means that the average monthly sales over the 5-month period is 13.8 thousand units. From a business perspective, this single value provides management with a quick summary of typical sales performance over the period. If any step in this calculation is unclear, please use the chat section to ask for clarification. We now move to the weighted arithmetic mean. The weighted mean is an extension of the arithmetic mean that recognizes that not all data values may contribute equally to the overall average. In many business situations, certain observations carry more importance than others, and weights are used to reflect this. The weighted mean is calculated by multiplying each data value by its corresponding weight, adding these products together, and then dividing the result by the sum of the weights. This approach ensures that values with greater importance have a larger influence on the final average. For example, suppose a business sells 3 products with different prices and quantities sold. Product A has a price of 10 and a quantity sold of 50, Product B has a price of 15 and a quantity sold of 30, and Product C has a price of 20 and a quantity sold of 20. To find the weighted mean price, each price is multiplied by its quantity sold, giving 500, 450, and 400 respectively. These figures are added to give 1,350, which is then divided by the total quantity sold of 100. The weighted mean price is therefore 13.5. This result shows that the average selling price, when sales volume is taken into account, differs from a simple arithmetic average. In practice, this is especially important for pricing analysis and revenue evaluation. The geometric mean is another important measure of central tendency, particularly when dealing with data that are multiplicative rather than additive. It is most commonly used when analyzing growth rates, ratios, and returns over time, such as investment performance. The geometric mean is calculated by multiplying all the data values together and then taking the nth root of the product, where n is the number of observations. This measure provides a more accurate average rate of change when values compound over time. To demonstrate this, consider an investment that records annual returns of 5%, 10%, and 12% over 3 years. These percentages are first converted into growth factors of 1.05, 1.10, and 1.12. These values are multiplied together to obtain approximately 1.2986. Taking the cube root gives approximately 1.0942. Subtracting 1 and converting back into a percentage gives 9.42%. This means that the average annual return, taking compounding into account, is approximately 9.42%. In investment analysis, this measure is preferred to the arithmetic mean because it reflects the true rate at which wealth grows over time. We now consider the harmonic mean. The harmonic mean is used when averaging rates or ratios, especially when the quantities involved are inversely related, such as speed, efficiency, or cost per unit. The harmonic mean is calculated by dividing the number of observations by the sum of the reciprocals of the data values. This measure is particularly useful in operational analysis and logistics, where rates are measured over equal units such as distance or output. For example, suppose a car travels at 60 km per hour and 120 km per hour over equal distances. The harmonic mean speed is calculated by dividing 2 by the sum of 1 divided by 60 and 1 divided by 120. This results in 80 km per hour. This value represents the correct average speed over the total journey, highlighting why the harmonic mean is more appropriate than the arithmetic mean in such situations. The median is another key measure of central tendency. The median is defined as the middle value of a dataset when the data values are arranged in ascending order. If the number of observations is odd, the median is the value in the middle position. If the number of observations is even, the median is calculated as the average of the two middle values. One of the main advantages of the median is that it is not affected by extreme values or outliers, making it particularly useful in skewed distributions. For example, in the dataset 5, 7, 9, 12, and 14, the median is 9, as it is the middle value. In the dataset 4, 8, 12, and 16, the median is calculated as the average of 8 and 12, which gives 10. In business contexts, such as income analysis or property prices, the median often provides a more realistic measure of a typical value than the mean when extreme values are present. The mode is the value that occurs most frequently in a dataset. A dataset may have no mode if all values occur only once, one mode if a single value occurs most frequently, or more than one mode if multiple values share the highest frequency. The mode is particularly useful when identifying the most common outcome or preference, such as the most frequently sold product or the most common customer choice. For example, in the dataset 3, 5, 7, 7, 8, 9, and 9, the values 7 and 9 both occur twice, so the dataset is bimodal. In contrast, the dataset 1, 2, 3, 4, and 5 has no mode because all values occur only once. In retail and marketing analysis, the mode can provide valuable insight into consumer behavior and demand patterns. Measures of central tendency have wide applications in business. In sales analysis, the mean or median can be used to calculate average sales performance, while the mode helps identify the most frequently sold product. In pricing strategy, averages based on historical data assist in setting competitive prices. In market research, these measures summarize consumer behavior and preferences. In investment analysis, the geometric mean is essential for evaluating long-term returns, and in efficiency analysis, the harmonic mean is appropriate for averaging rates, such as cost per unit or speed of operation. We now consider a practice question to consolidate these ideas. A retailer records the number of units sold daily over 7 days as 50, 60, 55, 65, 60, 55, and 70. To calculate the mean units sold, all values are added together to obtain 415 and divided by 7, giving approximately 59.29. To find the median, the data are arranged in ascending order as 50, 55, 55, 60, 60, 65, and 70, and the middle value is 60. To determine the mode, we observe that 55 and 60 both occur twice. So the dataset is bimodal with modes of 55 and 60. This example illustrates how different measures of central tendency provide different insights into the same dataset. If you would like to explore why one measure may be preferred over another in specific business situations, please raise this in the chat section. This brings us to the end of our discussion on measures of central tendency. I encourage you to reflect carefully on the purpose, calculation, and interpretation of each measure, and on how selecting the appropriate measure strengthens business analysis and decision-making. Please continue engaging with the material and make use of the chat section whenever you require clarification, in line with the flexible Synapse learning model. We now continue with descriptive statistics by examining measures of dispersion. While measures of central tendency tell us about the center of a dataset, measures of dispersion describe how spread out the data are around that central value. In business and accounting, understanding dispersion is just as important as understanding averages, because two datasets can have the same mean but very different levels of variability, risk, or consistency. As we go through this section, please remember that you can use the chat section at any time to ask questions or seek clarification. Measures of dispersion are statistical tools used to describe the degree of variation or spread in a dataset. They show how much individual data values differ from one another and from the central value. In business contexts, measures of dispersion are essential for assessing risk, volatility, stability, and reliability. For example, managers use dispersion to evaluate fluctuations in sales, variability in costs, consistency in production quality, and risk in investment returns. The main measures of dispersion covered in this section are the range, quartiles, deciles, percentiles, mean deviation, standard deviation, and coefficient of variation. We begin with the range, which is the simplest measure of dispersion. The range measures the spread of data by calculating the difference between the maximum value and the minimum value in a dataset. The range is equal to the maximum value minus the minimum value. Although the range is easy to calculate and understand, it is sensitive to extreme values and therefore provides only a rough indication of variability. In business analysis, the range is often used as a quick initial measure to understand the spread of sales figures, prices, or costs. For example, consider a dataset representing sales in thousands of units over 5 months, given as 10, 12, 15, 18, and 20. The maximum value is 20 and the minimum value is 10. The range is therefore 20 minus 10, which equals 10. This tells us that sales vary by 10,000 units over the period. While this gives a basic sense of variability, it does not tell us how the data are distributed within that range. We now move on to quartiles. Quartiles divide a dataset into 4 equal parts, with each part containing 25% of the data. There are 3 quartiles, known as the first quartile, the second quartile, and the third quartile. The first quartile represents the value below which 25% of the data fall. The second quartile is the median of the dataset, and the third quartile represents the value below which 75% of the data fall. Quartiles are useful because they provide more detailed information about the distribution of data than the range alone. For example, consider the dataset 10, 12, 15, 18, and 20. When the data are arranged in ascending order, the median or second quartile is 15. The first quartile is the median of the lower half of the data, which is the average of 10 and 12, giving 11. The third quartile is the median of the upper half of the data, which is the average of 18 and 20, giving 19. These values show how the data are spread across different sections of the distribution and are particularly useful in identifying skewness and outliers. Closely related to quartiles are deciles. Deciles divide a dataset into 10 equal parts, with each part containing 10% of the data. The first decile represents the value below which 10% of the data fall, the second decile corresponds to 20%, and so on, up to the ninth decile, which corresponds to 90% of the data. Deciles provide a more detailed breakdown of the distribution and are commonly used in large datasets, such as income distributions or sales performance rankings. For example, in a dataset of sales figures, the fifth decile corresponds to the median, representing the point below which 50% of the observations fall. In business, deciles are often used to classify customers, products, or regions into performance bands, such as top 10% performers or bottom 20% performers, which supports targeted decision-making and strategic planning. Percentiles extend the idea of deciles further by dividing a dataset into 100 equal parts. The pth percentile is the value below which p% of the data fall. Percentiles are widely used in market research, performance evaluation, and benchmarking because they allow very precise comparisons within a distribution. For instance, being in the 90th percentile means that a value is higher than 90% of all observations. As an example, consider again the dataset 10, 12, 15, 18, and 20. The 50th percentile corresponds to the median, which is 15. The 25th percentile corresponds to the first quartile, which is 11, and the 75th percentile corresponds to the third quartile, which is 19. In business analysis, percentiles are particularly useful for comparing individual performance against a broader population, such as employee productivity or customer spending patterns. We now turn to mean deviation, which measures the average distance of each data value from the mean. Mean deviation provides insight into how spread out the data are relative to the average. The mean deviation is calculated by finding the absolute difference between each data value and the mean, adding these absolute differences together, and then dividing by the number of observations. Unlike variance and standard deviation, mean deviation uses absolute values rather than squared values, making it easier to interpret intuitively. For example, consider the dataset 10, 12, 15, 18, and 20. The mean of the dataset is 15. The absolute deviations from the mean are 5, 3, 0, 3, and 5. Adding these values gives 16. And dividing by 5 gives a mean deviation of 3.2. This result tells us that, on average, the data values deviate from the mean by 3.2 units. In business, mean deviation can be useful for assessing consistency in performance or customer satisfaction scores. One of the most important measures of dispersion is the standard deviation. The standard deviation measures how far data values typically deviate from the mean and is widely used in business, finance, and economics. It is defined as the square root of the variance. Variance itself is calculated as the average of the squared deviations from the mean. Standard deviation is the square root of the sum of the squared deviations from the mean divided by the number of observations. By taking the square root, standard deviation is expressed in the same units as the original data, making it easier to interpret. For example, using the dataset 10, 12, 15, 18, and 20, the squared deviations from the mean of 15 are 25, 9, 0, 9, and 25. Adding these gives 68, and dividing by 5 gives a variance of 13.6. Taking the square root gives a standard deviation of approximately 3.69. This indicates that the data values typically deviate from the mean by about 3.69 units. In business analysis, standard deviation is commonly used to measure sales, volatility, cost fluctuations, and investment risk. Finally, we consider the coefficient of variation, which measures relative dispersion rather than absolute dispersion. The coefficient of variation compares the standard deviation to the mean and is usually expressed as a percentage. The coefficient of variation is equal to the standard deviation divided by the mean, multiplied by 100. This measure is particularly useful when comparing variability between datasets with different units or different average values. For example, if a dataset has a mean of 15 and a standard deviation of approximately 3.69, the coefficient of variation is calculated by dividing 3.69 by 15 and multiplying by 100, giving approximately 24.6%. This means that the standard deviation is about 24.6% of the mean. In business and finance, the coefficient of variation is widely used to compare risk between investments, assess efficiency across departments, and evaluate consistency in performance where absolute values differ. Measures of dispersion have many important applications in business. In risk assessment and investment analysis, standard deviation and coefficient of variation are used to measure volatility and uncertainty in returns. In quality control, measures such as range and standard deviation help monitor consistency in production processes. In market research, percentiles, quartiles, and deciles are used to analyze income distribution, customer spending behavior, and market segmentation. In performance evaluation, dispersion measures help managers understand whether results are consistent or highly variable across time, employees, or departments. As you reflect on this section, remember that measures of dispersion complement measures of central tendency by providing a fuller picture of the data. A meaningful business analysis always considers both where the data are centered and how widely they are spread. Please continue to engage actively and use the chat section whenever you need clarification, in line with the flexible Synapse learning model. We now continue with descriptive statistics by examining measures of skewness. Measures of skewness help us understand the shape of a data distribution, specifically whether the data are symmetrically distributed around the center or whether they are skewed to one side. In business and accounting, skewness is important because it affects how averages should be interpreted and how decisions should be made based on data patterns rather than isolated values. As we go through this section, please feel free to use the chat section at any point if you would like clarification. Skewness is a statistical measure of asymmetry in a distribution. A distribution is said to be symmetric when the left and right sides of the distribution are mirror images of each other, meaning that values are evenly spread around the center. When a distribution is not symmetric, it is skewed. A positively skewed distribution, also called right-skewed, occurs when the right tail of the distribution is longer than the left tail, indicating the presence of a few unusually high values. A negatively skewed distribution, also called left-skewed, occurs when the left tail is longer, indicating the presence of a few unusually low values. When skewness is zero, the distribution is symmetric, as is approximately the case for a normal distribution. Understanding the direction and magnitude of skewness is essential in business analysis because it reveals whether typical values are better represented by the mean or by the median. We begin with Pearson's coefficient of skewness, which is one of the most commonly used measures of skewness. Pearson's coefficient of skewness uses the mean, the median, and the standard deviation to quantify the asymmetry of a distribution. Pearson's coefficient of skewness is equal to 3 multiplied by the mean minus the median divided by the standard deviation. This formula links skewness directly to measures of central tendency and dispersion, making it intuitive to interpret in practical applications. A positive value indicates right skewness, a negative value indicates left skewness, and a value close to 0 indicates symmetry. To illustrate Pearson's coefficient of skewness, consider a dataset representing company sales in units, given as 10, 12, 15, 18, and 25. We first calculate the mean by adding all the values to obtain 80 and dividing by 5, giving a mean of 16. The median is 15, as it is the middle value when the data are arranged in ascending order. The standard deviation is calculated by first finding the squared deviations from the mean, which are 36, 16, 1, 4, and 81, summing these to obtain 138, dividing by 5 to obtain a variance of 27.6, and then taking the square root to give a standard deviation of approximately 5.25. Pearson's coefficient of skewness is then calculated by taking 3 multiplied by 16 minus 15 and dividing the result by 5.25, which gives approximately 0.57. This positive value indicates that the distribution is right skewed, meaning there are some higher sales values stretching the distribution to the right. In business terms, a positively skewed sales distribution suggests that most sales occur at lower levels, with occasional high sales days, pulling the mean upward. In such cases, managers should be cautious when relying solely on the mean, as it may overstate typical performance. Instead, the median may provide a more realistic representation of usual sales. This highlights why understanding skewness is critical for sound decision-making, particularly in planning, forecasting, and performance evaluation. We now turn to the product coefficient of skewness, which is a more mathematically rigorous measure based on the third central moment of the distribution. This measure considers how far data values deviate from the mean and the direction of those deviations, with greater weight given to more extreme values. The product coefficient of skewness is calculated by taking the sum of the cubed deviations of each data value from the mean, dividing this sum by the number of observations multiplied by the standard deviation cubed. Because this measure involves cubed deviations, it is particularly sensitive to extreme values and provides a detailed assessment of asymmetry. Using the same dataset of 10, 12, 15, 18, and 25, the mean is 16 and the standard deviation is approximately 5.25. The cubed deviations from the mean are negative 216, negative 64, negative 1, 8, and 729. Adding these values gives 456. The product coefficient of skewness is then calculated by dividing 456 by 5 multiplied by 5.25 cubed, which results in approximately 0.6. 3. This positive value again confirms that the distribution is right skewed, consistent with the result obtained using Pearson's coefficient of skewness. The interpretation of the product coefficient of skewness follows the same general principles. A positive value indicates right skewness, a negative value indicates left skewness, and a value close to 0 indicates a symmetric distribution. Because this measure is based on higher order moments, it is often used in more advanced statistical analysis and research, but it remains highly relevant in business contexts, where extreme values can significantly influence outcomes, such as financial returns or demand fluctuations. Measures of skewness have important applications in business. In market analysis, skewness helps businesses understand whether most customers fall into lower or higher spending categories. In sales analysis, skewness reveals whether revenue is driven by many small transactions or a few large ones. In investment analysis, skewness is used to assess the likelihood of extreme gains or losses, which is critical for risk management. In customer satisfaction analysis, skewness can indicate whether most customers are satisfied with a few dissatisfied outliers, or the reverse. In quality control, skewness helps identify whether production outputs are consistently centered or biased toward one side of the target value. We now consider a practice question to consolidate these ideas. Suppose a dataset of daily sales figures produces a Pearson's coefficient of skewness of positive 1.2. This indicates that the distribution is positively skewed, meaning that most sales values are clustered at the lower end, with a few high sales days stretching the distribution to the right. From a business perspective, this suggests that planning based on the mean alone may be misleading, and that inventory, staffing, and forecasting decisions should account for the fact that lower sales days are more common than the mean might suggest. If you would like to discuss how skewness influences real business decisions, please raise this in the chat section. This brings us to the end of our discussion on measures of skewness. I encourage you to reflect on how skewness complements measures of central tendency and dispersion by revealing the shape of the data distribution. Together, these descriptive statistics provide a comprehensive picture that supports accurate interpretation and informed decision-making in line with the flexible Synapse learning model. We now continue with descriptive statistics by examining measures of kurtosis. While measures of central tendency, dispersion, and skewness tell us about the center, spread, and symmetry of a dataset, measures of kurtosis focus on the shape of the distribution, specifically the extent to which data values are concentrated in the tails, or around the center. In business and financial analysis, kurtosis is important because it helps us understand the likelihood of extreme values, which are often associated with risk, volatility, and unusual outcomes. As we proceed, please feel free to use the chat section whenever you need. Clarification. Kurtosis is a statistical measure that describes the degree of peakness or flatness of a distribution compared to a normal distribution. More precisely, kurtosis measures the weight of the tails of a distribution, indicating how frequently extreme values occur. A distribution with high kurtosis has heavier tails, meaning that extreme values occur more often, while a distribution with low kurtosis has lighter tails, meaning that extreme values are less frequent. In business contexts, understanding kurtosis is crucial when analyzing financial returns, sales volatility, quality control data, and any situation where rare but impactful events can significantly affect outcomes. There are three commonly recognized types of kurtosis. A leptokurtic distribution has heavy tails and a sharp peak, indicating a higher probability of extreme values compared to a normal distribution. A mesokurtic distribution has a kurtosis similar to that of the normal distribution and is considered the benchmark case. A platykurtic distribution has lighter tails and a flatter peak, indicating fewer extreme values than a normal distribution. Recognizing these shapes helps businesses assess whether their data exhibit unusually high or low risk due to extreme observations. We begin with Pearson's coefficient of kurtosis. Pearson's coefficient of kurtosis measures the degree of kurtosis by comparing the fourth central moment of a distribution to the fourth power of the standard deviation. Pearson's coefficient of kurtosis is calculated by taking the sum of the fourth powers of the deviations of each data value from the mean, dividing this sum by the number of observations multiplied by the standard deviation raised to the power 4, and then subtracting 3. The subtraction of 3 ensures that a normal distribution has a kurtosis value of 0 under this measure. As a result, positive values indicate a leptokurtic distribution, negative values indicate a platykurtic distribution, and a value of 0 indicates a mesokurtic, or normal, distribution. To illustrate Pearson's coefficient of kurtosis, consider a dataset representing sales figures given as 10, 12, 15, 18, and 25. The mean of the dataset is 16, and the standard deviation is approximately 5.25. The fourth powers of the deviations from the mean are calculated as 11,236.64, 207.36, 2.0736, 23.57, and 697.26. Adding these values gives a total of 12,167. Pearson's coefficient of kurtosis is then calculated by dividing this total by 5 multiplied by 5.25 raised to the power 4 and subtracting 3. This results in a value of approximately 0.2. Because this value is positive but small, the distribution is slightly platykurtic, indicating fewer extreme values than a normal distribution. From a business perspective, this suggests relatively low exposure to extreme outcomes in the dataset. We now turn to the product coefficient of kurtosis. The product coefficient of kurtosis is another measure based on the fourth central moment, but unlike Pearson's coefficient, it does not subtract 3 from the final result. The product coefficient of kurtosis is calculated by taking the sum of the fourth powers of the deviations of each data value from the mean, and dividing this sum by the number of observations multiplied by the standard deviation raised to the power 4. Under this measure, a value of 3 corresponds to a normal, or mesokurtic, distribution. Values greater than 3 indicate a leptokurtic distribution, while values less than 3 indicate a platykurtic distribution. Using the same dataset of 10, 12, 15, 18, and 25, the sum of the fourth powers of the deviations is 12,167, the number of observations is 5, and the standard deviation is approximately 5.25. Dividing 12,167 by 5 multiplied by 5.25 raised to the power 4 gives approximately 0.65. Because this value is less than 3, the distribution is classified as platykurtic. This result is consistent with the conclusion obtained using Pearson's coefficient of kurtosis and reinforces the interpretation that the dataset has relatively light tails and fewer extreme values. The interpretation of kurtosis is particularly important in business applications. In investment and financial markets, high kurtosis indicates a greater likelihood of extreme returns, both gains and losses, which increases risk and uncertainty. In quality control, high kurtosis may suggest the presence of occasional extreme defects that require investigation, even if average quality appears acceptable. In marketing and sales analysis, kurtosis can reveal whether revenue is driven by a few unusually large transactions, or by more consistent, moderate sales. In forecasting and predictive modeling, understanding kurtosis helps analysts incorporate the possibility of rare, but high-impact events into their models, improving the robustness of business decisions. To consolidate these ideas, consider a practice question involving annual returns on investment of 5%, 10%, 15%, 20%, and 30% calculating the product coefficient of kurtosis for this dataset results in a value of approximately 0.65, which is less than 3. This indicates a platykurtic distribution, meaning that extreme returns are less frequent than would be expected under a normal distribution. For a business or investor, this suggests relatively stable returns with a lower likelihood of extreme outcomes, although this conclusion should always be considered alongside other measures such as mean, standard deviation, and skewness. This brings us to the end of our discussion on measures of kurtosis. I encourage you to reflect on how kurtosis complements measures of central tendency, dispersion, and skewness by providing insight into the likelihood of extreme values. Together, these descriptive statistics offer a comprehensive framework for understanding data behavior and supporting sound business and financial decision-making. Please continue engaging with the material and make use of the chat section whenever you require clarification, in line with the flexible Synapse learning model.